Hey everybody, today we have two presentations for you from Tennessee Tech University. Tennessee Tech is one of the partnering institutions of the SMARTT grant. As a university, we are pretty much active in the additive manufacturing technologies, and the talk we have for you is on the advancements of additive manufacturing, especially in the composite manufacturing. Smart manufacturing is one of the key topics of US manufacturing lately, and inside it, as you all know, additive manufacturing is the main component. In our presentation today, we will highlight two of the very fresh, very new composite printing technologies. Ankit Gupta and Hasanov are the PhD candidates in the mechanical engineering department. They will highlight their latest research and advancements in the composite 3D printing technologies for you. Ankit, let's have you first and Seymour second.
So good morning, everyone. My name is Ankit Gupta. I'm a PhD candidate in Tennessee Technological University. So I'm working on Dr. Ismail Fidan as a PhD student. So my topic for you today is fabrication and characterization of short fiber reinforced composite parts using fused filament fabrication process. And so first I will talk about the fiber reinforced additive manufacturing. So this is a term we use, and this is the research we do in our lab. So I will discuss this technology with you today. So as we all know, what is additive manufacturing? So I will give first overview what is additive manufacturing. So additive manufacturing is a technology to create three-dimensional objects with the help of layer upon layer addition of the materials. So there are so many additive manufacturing processes available in the market. So currently there are 7 additive manufacturing processes available, but we in our lab work on the fused filament fabrication process. This is one of the well-known additive manufacturing technology, and this is widely used in research labs and in the industries and in the major medical sector as well. So there are so many benefits of this technology, like it helps in reducing the weight of the overall part. It generally takes less lead time. It helps to produce a low cost part, and you can also build a complex part with the help of this technology. So as we all know, like there are some applications available in the market that cannot be there, like property fulfillment cannot be made with the single material. So you have to use 2 different materials to fulfill the needs of that applications. So in order to fulfill that need, fiber reinforced additive manufacturing comes into picture. So what is fiber reinforced additive manufacturing? It is a club of 2 different materials. So one material is as a base material, and other material as a we use as a reinforcement to increase the properties of the final part. So what are the benefits of FRAM? So now we have to discuss what benefits this technology is giving to us. Fiber reinforced additive manufacturing offers a various solutions to some problems currently we are facing in the industries and in some research areas, like low mechanical properties. The parts now have some issues in the mechanical property. They are not meeting the mechanical property requirements. So more weight, that is also the issue, and low thermal properties. But fiber reinforced additive manufacturing helps in resolving these issues, as it combines the flexibility of additive manufacturing and the advantages of the composite material. As you can see in the figure, this is a FFX technology I am showing in the figure. So this is a very simple technology. It is just, I discussed, it's a bead by bead printing, layer by layer manufacturing of the part. So what we do is we feed the material inside the heated chamber, and then we melt that material inside that chamber, and then we do the printing. We do the layer by layer extrusion of that material which we are feeding. This is a very simple process. Now, the question is, there are so many fibers available. As I say, there are so many forms of fibers, reinforcements currently available in the market. But the question is, why we are sticking to short fibers. Like we have long fibers, we have continuous fibers, we have short fibers. And why short fibers? Like what are the advantages of short fibers? So first of all, I will discuss three main important benefits of using the short fibers. First is it is very easy to manufacture. First, second is very important. It is cheaper than the other fibers like continuous fiber. It is way cheaper than the continuous fibers. And the third is also very important. Like we know that the parts, the structures we use in industries, in other areas, in other industrial areas, they are not like only simple shaped parts, right? Not a simple shaped structures. There's so many complexities available in the structures. So what are the solution? So, and we need a good properties for those structures as well. But it's hard for the conventional manufacturing to build those complex parts and to build with the only single materials. But short fibers has the tendency, if you put that short fibers in any form of polymer material, you can create any complex part without any difficulty, as we face in the continuous fibers and in the long fibers. So that is the main advantage of short fibers. So I will just, as I told you, like there are so many fibers available, forms of fiber, continuous, long and short. Now I will discuss with you how we create these short fibers filaments. So this is the filament generation process we do in our lab. We don't buy these filaments from outside. First of all, there are two reasons for that. First, from outside, they are very costly, way costlier than what we produce in our lab. Second is, there is a limited modification you can do in the filament in terms of fiber percentage. You can get from the market with only specific percentage level, but in here in our lab we can produce some various percentage composite filaments, and it's very cheap. So that's why we do this in our lab in order to reduce the final product cost. So I will discuss with you how we create the composite filament step-by-step process, and it's a very easy process. So I will start this thing. So what we do is we take two different materials, one as a base material, which we call as a matrix, and the second is the reinforcement materials, which we take in the form of fibers. You can take powders as well. It depends upon the application. So in this, we took the fibers as a reinforcement and the polycarbonate. This is one of the thermoplastic, very high temperature thermoplastic, and we took it as a base material, which we call it a matrix. What we do is we take those two materials, mix them properly, thoroughly, and then we dry them in a furnace. Why we are drying these materials? Like that is the question generally people ask. So generally we do the drying of these materials to get rid of the moisture. This is a very important step in any part production, because if moisture is present in the materials, it will eventually degrade the quality of the final part. So we have to, whatever material we are using, we have to dry them for 7 to 8 hours continuously. So that's why we do the drying. First, we take the material, we dry them for 7 to 8 hours continuous at particular temperature below the melting point of the material which we are using. So that's okay. Then after drying, then we shift this dried material mixture to the extruder. Now this is in third picture you are seeing, this is the machine which helps to create the composite filament. It has 3 sections. I will discuss one by one. First is extruder section, where we pour the material mixture. Second is the air path, that helps to dry that composite filament coming from the heated region. This drying is very important. This cooling is very important. It helps to eventually, it helps in creating the exact uniform diameter for the composite filament. So this step is very important, and we have to regulate the air path speed as well. So, okay, then third section is the spooler. This spooler helps to spool those filaments what we are extruding, so that we can we can fit that to any 3D printer of this, any desktop 3D printer. Okay. So what we do is like, I will discuss how it works. We first pour that dried material mixture into the extruder, first section. Here we melt those material mixture. Okay, then we force that material to come from the orifice of the nozzle, from that extruder. Then it comes to the air path section. That is the second step. Here we cool down those heated filament. Okay, then we shift that material to the spooler section. It has to spool that composite filament for easy transferring and easy adjusting to the 3D printer, any 3D printer. Okay, so this is how we do the creation of the composite filaments to build any composite structures. Now, this is the one of the problem actually I faced, like warping problem. So in order to reduce that warping problem, what is warping actually? So this problem we generally face in the high temperature polymers. Like, so if you are using any if you want to use the part in the automobile sector, and you know automobile sector generally requires the high temperature materials. They work on very high temperatures, right? So, but the problem with the high temperature materials, if we use in the 3D printers, they warp. As you can see in the figure A, they warped. If they warped, the quality, the mechanical performance of that part is going to be bad. So you can't use that material. So you have to resolve that warping issue. So in our lab, we figure out this procedure, this technique to reduce that warping situation is closed chamber printing. So what we are doing, we are regulating the surroundings of the 3D printing. So we did the two researches, one without controlling the surrounding temperature of the 3D printer, and one with the surrounding, by controlling the surrounding temperature. As you can see in the figure A and B, A is without controlling, B is with controlling. You can see in figure B, you are not seeing any warping. So what we did here is like we did the 3D printing of composite parts in a closed chamber by maintaining a 50 degrees Celsius around it. That helps in reducing that totally eliminates the warping of the high temperature polymers, and the mechanical performance also gets improved. So this is the step we used for high temperature polymers if you want to use those polymers in the automobile sectors. Okay. Now, process description, as I already discussed some portion of this process before, but I will give you one more time the overview. So what we do is like we take two different materials. Okay, and you can take two different polymers as well. You can take any polymer and reinforcement in the form of fibers, powders. Okay, you can take any two polymers, two materials. Okay, then we dry them, then we shift it to the extruder, and we create, when we convert this material, like in the material into the filament form, because generally most of the 3D printers, 3D printing technology generally use filament as a raw material. So you have to convert the pellets or powder or fiber into the filament form. So okay, so we create the composite filament with the help of extruder, then we spool them, then we transfer it to the 3D printer, then we do the 3D printing of the composite structures. So this is the entire process. Now, like microstructure analysis. So I told you that we generally use two different materials for increasing the properties of the final part, right? But the question is, which two materials? Like why we use polycarbonate and short carbon fibers, right? Means like why you choose those particular two materials, right? So we have to check, are they these two materials which we chose, are they compatible to each other or not? Like it's not like that we can choose any materials, like any two different materials, just mix them and you can do the 3D printing, you can create any structure. So you have to check, you have to check, like are they making good bonds with each other or not? Because bonding between any two materials is very important to ultimately increase the final properties, right? So what we do is we do the microstructure analysis using SEM. So as you can see in the figures, I did the microstructure analysis for the polycarbonate and the short carbon fibers. As you can see, they are like insignificant gaps at the interface of the polycarbonate and the short carbon fibers. So means these two materials are well compatible to each other, and we can use this composite filament for building any automobile part or any part of related to any industries. Okay, so we verified that. So this is one of the steps we have to follow all the time. These are some experimental parameters we generally use for 3D printing and filament creation. So I will tell you some basic important parameters like in the 3D printing. First is the bed temperature for proper sticking of the part to the bed. Extrusion temperature to melt that material, composite filament. And the closed chamber I already discussed with you, like we have to maintain the some temperature around the 3D printer, and the printing speed, how fast you want to print it. It's up to you only. And the table 2 shows you the extrusion parameters. So you have to adjust the extrusion temperature, air pass speed, extrusion speed. Okay, so I already discussed like these, how there are 3 steps, right? Extrusion, air path, and extrusion speed. So we have to adjust the parameters accordingly. Filament diameter, generally the 3D printers available in the market requires two different forms of diameters, 2 types of diameters we generally use in the 3D printers available in the market. One varies from 2.65 to 2.85, another varies from 1.65 to 1.75. So whenever you are going to buy the filaments from the market, or you are producing by yourself, you have to check that range. Your filament should be in that range only. Okay, then you can use those materials in any 3D printer in the world. So as I discussed, like we generally do these composite analysis for good mechanical properties, right? To achieve the good mechanical properties. So I'm showing you just one of the testing I performed just to validate that, like after putting the reinforcement, am I getting the good properties or not? As you can see in the bottom 2 graphs for flexural strength and flexural modulus, as you are keep on increasing the fiber percentage in any material, I use the polycarbonate, the properties are increasing. Okay, so if you put more reinforcement, property will increase. Okay, so that's how we fulfill the needs of the structure part which we use, which we are going to use in any industries. Okay, see, there are some applications where we can use the FRAM technology, fiber reinforced additive manufacturing. As you can see, these parts are very, very complex, right? So you can't use any continuous fibers to build these kind of complex structures. So you have to use the short fiber reinforced additive manufacturing process to build these kind of complex structures. As I discussed, why that is the reason I chose the short fibers as one of the reinforcement. So as you can see, like these are very, very complex parts, right? And fused filament fabrication is the only technology that has the tendency to build these complex parts. So now what we are doing, we are merging these 2 things, short fibers and the fused filament fabrication. So by combining those, you can print any complex part with good mechanical properties, with good mechanical performance. So we printed some dentures with that technology, fiber reinforced additive manufacturing. See, these parts are very, very complex. It's very hard to build these complex dentures with any other technology. So additive manufacturing has that capability, fused filament fabrication has that capability. So and short fibers, what benefits short fibers are giving? It helps in increasing the clinical properties of these dentures. So what we are fulfilling the demands of industries, what they require: good mechanical properties, complex part production, easy production. So we are fulfilling all the demands of the major industries with this fiber reinforced additive manufacturing technology. So that's it from my side. Thank you so much for listening. Thank you so much.
Hello, everyone. Today I'm going to talk about conventional multi-material versus functional graded additive manufacturing. Ankit talked about composites and fabricating using a fused film fabrication process. And I'm going to talk about, again, these are composites. A multi-material structure is a type of composites. but I'm going to talk about mainly functional graded materials. Okay, let's take a look at what's functional graded material. Functional graded materials are advanced engineering materials that present complex spatial varying material properties. And functional graded materials occur naturally, actually occur in nature as bones, teeth, and nature designed these materials to meet their expected service requirements. And this idea is emulated from nature to solve engineering problems. For example, if we take a look at a human bone, we will see that it has a functional formation. For example, in these materials, the change of material distribution contributes to property and functional deviations. And in one structure, it has a principal compressive load groups, and on the other side, we see that there is a principal tensile groups, and which these materials helps to increase their service requirements. Okay, how we can produce these type of materials? Uh, we have two types of system to produce multi-material structures, and what we refer conventional multi-material additive manufacturing and functional graded additive manufacturing. As you see the schematics of these processes, FGAM is a layer by layer fabrication process that intentionally modifies the processing parameters and gradually distribute materials within one component to meet the intended function. And it can be seen that in conventional multi-material AM, we use two different nozzles to fabricate two materials, which result one single structure, but with a discrete material interface boundaries. And on the other hand, in functional graded additive manufacturing, we see that materials are fed in one melting chamber, which allows to vary the composition of material in one structure, so that we can eliminate discrete boundaries in one structure. Okay, what type of system we use in our lab? We have two types of systems, like a Z-Morph multi-tool 3D printer, which allows to fabricate functional graded materials. It allows to mix two materials together in one structure with continuous interface boundaries. And we have Ultimaker dual extrusion system as well, which we refer conventional multi-material AM system, and that uses two different nozzles to fabricate multi-material structures. In Z-Morph technology, where we bought it from Profound 3D company, which is a Z-Morph reseller in USA. And Z-Morph, with the help of Z-Morph multi-tool 3D printer, the print head can be easily changed to other heads as well. Like you can produce single material fabrication, you can use multi-material fabrication, you can perform CNC machining as well. And also you can do laser engraving, thick material paste extrusion as well. So it's a multi-tool 3D printer. This is what we use in our lab. Let's take a look at the dual pro extrusion head using Z-Morph technology. And in a schematic way, we see that it uses only one nozzle, but we have two material inlet options, which allows to feed two materials in one mixing chamber. In that mixing chamber, we have a static mixer that allows to fabricate blended materials in one single structure. Okay, we did some experimentation just to compare conventional multi-material and functional graded multi-material processes. So we chose three different materials over here, and we designed dissimilar and similar material interfaces. Over here, we refer to FGM as thermoplastics and FGM as composites. And we use ABS material, ABS polycarbonate, and short carbon fiber reinforced ABS materials, which all these are commercial available materials, and they are widely used in 3D printing in the 3D printing industry. Why we chose ABS? Because it's ABS and polycarbonate, they are widely used, and their melting temperature and glass transition temperature allows to fabricate these two materials in one in one mixing chamber. Actually, ABS is a very broad class of copolymers. It's an amorphous material. It doesn't have a true melting point, but according to the MATFAB, as you see, the melting temperature varies from 210 to 343 degrees Celsius. And for polycarbonate, for ABS, it varies from 170 to 320. So actually, based on the information provided, we see that doesn't have a polycarbonate is amorphous polymer as well. So it doesn't have a true melting point. Depending on application, we can decide, we can use these materials in our fabrication. And nozzle temperature, what we have a balanced temperature range. So we decided to fabricate our structures, to print our samples with 250 degrees Celsius, so that we can mix polycarbonate and ABS in one melting chamber. And we use tensile testing method to characterize interfaces of these materials. Okay, let's take a look at interface strengths. And we design 3 different interface transition patterns to test using tensile testing method. According to results, the gradient transitional materials showed higher tensile strengths and stiffness than the direct and interlock mechanism. We added interlock as well because we want to check how interlocking will help to increase the strength and stiffness of the conventional multi-material printed parts. And here, since actually the material transition occur gradually, this in FJM made parts, the gradual transition helps to reduce stress concentrations at material interfaces. However, the abrupt change of material properties at direct and interlock patterns increase the stress concentrations, and therefore delamination occurs at the interface. So gradient transition showed, according to the results, 120% and 108% higher tensile and stiffness result than the direct and interlock transition respectively. And gradient transition yielded 15% and 8% higher stiffness behaviors than the direct and interlock transition. Since these are different polymers, so we use polycarbonate and ABS, let's take a look at the transitioning in these materials. In gradient transition, the material changed gradually from polycarbonate to ABS, as you see over here. But on the other hand, we have a direct transition in conventional made additive manufactured parts. So the red arrow shows the load applied perpendicular to the bead direction. This is the formation of fused filament fabrication made parts. In gradient transition, we see that we have similar material interfaces. So we have ABS, for example, 60% meets with ABS 40%, which they have higher entanglement of ABS polymer chains. And for polycarbonate side, we have this is more in polycarbonate. Polycarbonate to polycarbonate bead to bead adhesion is more than the polycarbonate to ABS interfaces, because we see that in gradient transition, the intermolecular diffusion starts in the mixing chamber, and this is at relatively higher temperatures. And in direct transition, what we see over here, the transition starts after depositing one layer in one nozzle. Then we shift the nozzle, we start to deposit the second layer. This depends, and this might help, this might reduce the intermolecular diffusion between polycarbonate and ABS materials. Therefore, in gradient transition, we experience better diffusion between materials, and also the gradual change of material properties helps to reduce the stress concentrations. Okay, let's take a look at the interface strengths of similar material interface. Because we have CF ABS, matrix material is the same, and ABS is just a simple ABS material. And we designed and tested these similar interfaces, and results reveal that although the matrix material is the same, the sharp transition of material properties increase the stress concentrations, which reduce the strength and stiffness of the part. Likewise, gradual change of material properties increase the strength around 58% and stiffness around 6%. Okay, we can also test the lengths of gradient transition as well. And the length of FGM transition increased to 10%. However, 10%, what we refer, it's the length, the length percentage of the total length. So if our test cell sample is 165 mm length, the 10% we refer that length at the middle of the specimen. It shows that if we increase the gradient transition, we get more strength, around 84%, and stiffness 5% as well. Stiffness doesn't change that much, but we increased the 84% in tensile strength. This shows that if we keep increase the gradient length inside the gauge region, we can get more strength values. We can enhance the material property. And also material property enhance 17% from at 10% FGM than 5% FGM. Okay, in conclusion, it was observed that the gradient transition showed a relatively higher interface strength than the direct transition between the similar material interfaces. And the same trend was observed in similar material interface as well. And it was revealed that the increase in transition length might increase the bonding strength and reduce the stress concentrations. And this study showed that although the base material is similar, the abrupt change in material properties increases the stress concentrations at multi-material interfaces. And gradual change over here in material properties reduces the stress concentrations at multi-material interfaces. And which show that with the help of FGAM method, we can enhance the bonding strengths between similar and dissimilar materials. This is my presentation. Thank you for listening.
Thank you, Ankit. Thank you, Seymour. Attendees, we were able to present you two different technologies today: how to make a short carbon fiber enhanced filament. And what we do is usually filament extruder, and we make our filaments with it, and then end of it, the parts we produce with these short carbon fibers are way stronger and sustainable than regular FFFF printers. The second one is a functionally graded materials technology that we've been using in our lab with the Z-Morph printer. As Seymour mentioned, this printer is a cutting-edge technology. It's called hybrid technology with not only the 3D printing, but also laser engraving and CNC machining. And the parts that we produce, end of it, is very successful in terms of mechanical characterization and a number of other testing we've done, including microstructural level. If you have further interest, we'll be more than happy to have you in our labs at Tennessee Tech University. We have a number of projects going on in workforce development and additive manufacturing innovation. And you're more than welcome to see what we do and how we do and collaborate with us or learn more. Thank you for the listening. If you wanted to learn more about things we do, the bio of Ankit and Seymour are available in your handouts or program. Just go ahead and communicate them. They'll be more than happy to provide you further information. Thank you.